since it's a cinematographic masterpiece, I'll have to move the camera. But anyway, so limb darkening. Here's a white light photograph of the sun, and you can see that the limb, the edge, is a bit dimmer than the center. And we talked about that before, the idea being you can see essentially to the same distance along the line of sight, no matter where you look. But if you're looking at the limb, the line of sight is coming in at an angle to the surface, and so the same distance along the line of sight doesn't get you as far towards the center, it doesn't get you as deep into the star, and so at the limb you're seeing down to higher, cooler layers, and at the center you're seeing down to higher, deeper, hotter layers. Because you're looking straight down, and so you're seeing hotter material looking at this center than you are at the limb, hence limb darkening. Now we can be a little more specific when we say that the effective temperature of the radiation you see is the actual temperature of the material at an optical depth of 2/3. So here's this figure from your book where we've specifically labeled that line of sight towards the star center. You see radiation that is at an effective temperature equal to the actual temperature of the layer whose optical depth is 2/3. And if you look near the limb, the line of sight doesn't get as far into the star to reach the layer where the optical depth is 2/3 along that line of sight.
So you're getting temperatures which are less even here.
Exactly. So the effective temperature near the limb is lower than the effective temperature near the disk center. So in other words, it's the same thing we said before, but we've been a little more specific and said, yeah, you see radiation characterized by the layer whose optical depth is 2/3 along the line of sight, but those are different layers within the star for different lines of sight. This is what it comes down to. Hence, limb darkening. And the other thing we can do is be more specific about how absorption lines are formed. So I will turn the lights back on and start talking about that on the board. So, the kind of first approximation to where absorption lines come from is the idea that we know that if we have a cool gas in front of a source of continuous radiation, of continuum radiation, that you'll see absorption lines because the atoms in the cooler gas absorb some of the photons coming from the layers producing a blackbody radiation spectrum, essentially, or at least a continuous rainbow spectrum. And they absorb those photons, and then they'll re-emit some photons when they drop back down to their original energy level. But in general, it won't still be going in the same direction as the radiation was originally. It'll be off in random directions, and so you're losing photons from the beam. And so that's the idea of the so-called reversing layer, where you've got the sun's cooler outer atmosphere serving as the cooler gas in front of the continuum radiation from the deeper, hotter layers below, and the reversing layer, quote unquote, absorbs some of the wavelengths and produces the dark spectral lens. That's kind of the simpler first approximation to what's going on. But we can we can now give a more detailed picture of what's going on. So if you were to plot absorption coefficient, kappa lambda, as a function of wavelength, then what you'll see is spikes at the wavelengths of spectral lines, because the gas is really good at interacting with light at spectral line wavelengths, because those atoms are really good. They have a very high cross section for absorbing photons of those wavelengths. So, and the spike, I do them all kind of the same height, but they're not. They'll be different heights because some atoms are better at absorbing at those wavelengths than others. And remember that d tau lambda is equal to minus kappa lambda rho ds. Right, that was our definition of tau lambda. So tau lambda itself came from integrating that. So we integrate that to get the optical depth, right? And the point is this then. So imagine that we want to plot brightness of the star, specific intensity coming out of the star as a function of wavelength. Okay? And overall, it'll look largely like a black body spectrum, but a bunch of dips where there's spectral lines. So let's look at some narrow range of wavelengths. What we see is something like there's an overall continuum level, but then there are sharp dips at the wavelengths of spectral lines. So this is a plot of brightness versus wavelength. If you turned it into a photograph, you'd have rainbow with dark lines superimposed on it. So what is going on there? At every wavelength, let's make it actually f lambda instead. At every wavelength, the flux we're seeing, using our rule of thumb, is what we would see for the layer at an optical depth of 2/3 at that wavelength, right? At wavelengths of spectral lines, where the opacity is much higher, an optical depth of 2/3 is closer to the surface of the star. Does that make sense?
Yeah.
Because if kappa lambda is much higher, you don't have to go as much ds to get the same overall optical depth. So we can say f lambda corresponds roughly because, again, there's the Eddington approximation, et cetera, but we're going to use this rule of thumb that works out to be about right even when you don't have the Eddington approximation being made and so forth. roughly speaking, the flux we see at each wavelength corresponds to what we see from the layer at optical depth 2/3 at that wavelength. This layer is closer to the surface and kappa lambda is larger. If I compare two wavelengths and one's got a larger kappa lambda, 2/3 optical depth of 2/3 is closer to the surface. So my cap, I'll catch it there. So when kappa lambda is larger, we see cooler layers close to the surface. In other words, what I want to say here. F lambda is smaller where kappa lambda is large. And that's what we're seeing here. At wavelengths where kappa lambda is large, the light isn't as bright because we're seeing higher, cooler layers. The effect is strongest right in the middle of an atomic transition wavelength, because there the opacity is very large. The star is very opaque in the middle of a spectral line, and so that means we're seeing layers closer to the surface. That's why a star has absorption lines. It's because the temperature is increasing as you go down into the star. And at spectral line wavelengths where the opacity is high, we don't see as far into the star, so we're seeing cooler, darker layers at spectral line wavelengths. That's why stars have absorption lines. Dark absorption lines result from seeing higher, cooler layers at atomic transition wavelengths. Where kappa lambda is very large. And so optical depth 2/3 is closer to the surface. So what if the entire star was all at the same temperature? Would you still see spectral lines?
If it was all at the
If it
same
was all at the same temperature. Would it still be true that at spectral line wavelengths you could not see as far into the star, where the opacity is very high at those spectral line wavelengths?
You wouldn't,
Why not?
because if the opacity is large,
So the opacity here is still going to spike up at atomic transition wavelengths because it's very good. The atoms are very good at absorbing those wavelengths.
because of the cross section.
So the opacity would still spike at spectral line wavelengths. The mean-free path would be very short because the photons are, the atoms are very good at absorbing those photons. So the opacity would still spike up. So it would still be true that at spectral line wavelengths you were seeing layers closer to the surface than you were at so-called continuum wavelengths, which do not correspond to spectral lines, and the other sources of photon scattering and absorption are in play. Free, and bound-free, and electron scattering as opposed to bound-bound. So we still see higher layers at bound-bound transition wavelengths. If the whole star was at the same temperature, would we see absorption lines in that case? Wow. So you're still not seeing as far into the star, but the whole star is the same temperature. So at a spectral line, so let's say that this is the top of the atmosphere. And let's say at a continuum wavelength, I'm seeing down to here. And at a spectral line wavelength, and again, seeing to an optical depth of 2/3, sloppy tisk, whatever. So let's say optical depth 2/3 here at the continuum, and the optical depth is 2/3 at a spectral line wavelength here.
Okay.
At a spectral line wavelength, I see down only to here, and at a continuum wavelength, I see down to here. If temperature increases with depth, then this layer isn't as hot as this layer. So if temperature increases with depth, I see a dark spectral line at an atomic transition wavelength, because at that wavelength I'm only seeing this higher, cooler layer, and at other wavelengths I'm seeing this deeper, hotter layer. Now what if everything's the same temperature?
Oh, okay, I see what you mean.
If everything's the same temperature,
you're gonna see all the way down.
No, it's still true.
Oh, you
it's still
with that
true.
spectral line wavelength, you only see till that depth.
Right. You'll see that depth close to the surface. Okay, well, if everything's the same temperature, how does the radiation coming from this layer compare to the radiation coming from this layer?
They're equal.
They're equal. So will you see a dark line anymore? No, because everything's at the same temperature, so it doesn't matter how far you see into the star, you're still seeing the same temperature.
I see.
Yeah. So in other words, stars have absorption lines because temperature increases with depth in the atmosphere, so that when you can't see as far into the star, you're seeing cooler, darker layers. If the whole star were the same temperature, that wouldn't happen because all the layers have the same temperature. You would see a continuum. In other words, if the whole star was the same temperature, you would just see a black body spectrum.
Yeah.
You wouldn't see dark lines anymore because everything's at the same temperature. So that we see spectral lines from a star is a consequence of it not being in thermodynamic equilibrium. In thermodynamic equilibrium, everything has to be at the same temperature. Spectral lines are characterizing the fact that it's not in thermodynamic equilibrium, that the temperature is increasing as you go deeper inside the star, and therefore decreasing as you get closer to the surface. So that's worth carefully pondering and be sure that you fully understand it.
Yeah, this was, I might have to go through this.
Yes, it's worth going through this, and there will be a homework problem that says, what will happen if the temperature were to decrease inwards instead of increase inwards? So thinking about that will be instructive.
Thank you.
And in fact, one way that we study the detailed structure of the sun's atmosphere, for example, is you can use very, very narrow band filters, such that they are narrower than the bandwidth of a spectral line. And so then what you can do is, as you scan, as you move the passband across the wavelength of the spectral line, if you're at the central wave of the spectral line, you're seeing high up in the atmosphere. And as you move away towards what we call the wings of the spectral line, where the opacity is not as large, you see deeper and deeper into the atmosphere. And so what you can do is essentially by taking, you can even do it with photographs, through very narrow band filters, you can take pictures of different layers in the atmosphere and get some detailed information about the atmospheric structure as a result of that.
And you wouldn't be able to do this exactly if it was all at the same temperature.
Yeah, you wouldn't be able to do that. If everything was the same temperature, you'd just see a black body spectrum essentially. Yep. Okay, so now I want to talk in some detail about the structure of stellar spectral lines, more details about how they work. Talk about what's known as equivalent width, which is a measure of the strengths of spectral lines. You know, we talked about classifying stellar spectra, and that talked about this. Yeah, we did that, right? We talked about A, O, B, A, F, G, K, M. Yeah, because I'm forgetting what, because I'm teaching astronomy 111 too, and so I'm like, wait, we did that in that class. Did we do this? So we talked about the strengths of the hydrogen lines, being stronger in A stars, weaker in other stars, and even in the sun, yeah, they're very weak. The hydrogen line is very weak, but it doesn't mean that the sun is not a lot of hydrogen, right? Because they're talking about Boltzmann, Zaha. Okay, yeah, I'm not forget. And by strengths of the spectral lines, we just kind of said, yeah, how dark they are. Now we'll be more specific about what we mean by that. What we really mean is we're talking about the equivalent width, it's called, of the spectral line. So, structure of spectral lines. So I'm going to make a sketch here. There's wavelength, and here we're going to have F lambda over Fc, flux at wavelength lambda over Fc, and actually let me just write it that way normally. F sub c is the continuum flux. In other words, the flux not at spectral line wavelength. So let's say outside the spectral line. Now the continuum flux looks roughly like a blackbody curve, but for any one wavelength, it's nearly constant at wavelengths just a little shorter and a little longer than the wavelength of the spectral line. So we're going to say, okay, we're going to plot the ratio of the flux of wavelength lambda to the continuum flux. So outside the spectral line, that will be 1 when we're in the continuum. And then as we move in towards wavelengths covered by the spectral line, spectral lines are not infinitely narrow, and so you'll get something like that, a dip where there is a central wavelength of the spectral line where it's at its darkest, and that'll in general be the canonical energy level difference between the two energies involved in the transition. So like, for example, the energy difference between n equals 3 and n equals 2 in hydrogen converted into a wavelength, lambda naught would be the wavelength of that transition. But because of various effects that we'll discuss, including the fact that energy levels aren't perfectly well defined, spectral lines are not infinitely narrow, You don't have to have exactly that wavelength to cause the transition.
And
That wavelength is the most probable to cause the transition, but you can be a bit off from that and still cause the transition.
it's a range.
Partly because the wavelength, the energy of the transition itself isn't perfectly well defined. In quantum mechanics, energy levels aren't perfectly well defined in general. And because of things like the Doppler effect. In other words, if the atom is moving towards you, your wavelength, the wavelength that I see won't be the same as the wavelength the atom sees. And so you'll also have a spread due to the motion of the atoms. So that's the generic kind of plot of what the spectral line looks like. And at any given wavelength, this represents what we call the depth at that wavelength, the depth of the spectral line at that wavelength. In other words, how far is it fractionally below the continuum? So the depth is the continuum wavelength minus f lambda divided by the continuum wavelength. That's what I illustrated there. So it's 1 minus f lambda over fc. And we'll note here that the depth is equal to 0 if f lambda is equal to fc. So in other words, over here, where we're back at the continuum flux, it's reasonable to say that the depth is 0 there. We haven't excavated at all, so to speak, a wavelength like that. And the depth is equal to 1 if f lambda is equal to 0. In other words, it never is, but if the flux were all the way down to 0, then you would get 1 minus 1 is 0. 1 minus 0 is 1 in that situation. And so you'd be all the way at the bottom here.
Right.
So you just read it off the scale. Here the depth is about 0.6, for example. Okay? So that's what we mean by the depth at a given wavelength. The middle part of the spectral line is called the core. So there's no hard and sharp boundary. The middle part of the spectral line is called the core. And the outer parts are called the wings. It's just terminology. It's kind of like, the bird spreads its wings. So I think somebody thought it kind of looked like wings coming off of a bird or something.
Let's see. So that core and wings don't refer to any part of the star, right?
I'm sorry?
The
No, so this has nothing to do with,
term.
so this is, we get the spectral line from the entire star. We're getting light from the entire star. If it's the sun, we can image a small part of it and get a spectral line from a little part of the sun. But when we look at stars, we're just getting light from the whole star. So this is the output of a spectrometer. This is you've scattered the light, you point a telescope at the star to gather light from it. You pass that through a slit and then shine that on a prism or on a diffraction grating and spread it out into a rainbow so that you can see the spectrum. And this is just a small part of the star spectrum that we've plotted here. So this is an output of a spectrometer. After we divide by a continuum. So you process it to generate this from the spectrometer's output. And then we can characterize, if you will, the strength of a spectral line by what called the equivalent width, W, of a line is the width delta lambda, in other words, how broad in wavelength the line would be, of a completely black line that has the same area over the curve, so to speak. In other words, if I found the area, if I integrated to find the area under the dashed line of the spectral line, then the equivalent width is the how wide a completely black spectral line would be that had the same area under it. In other words, a spectral line whose depth went from 0 all of a sudden to 1, stayed 1 for some range, and then jumped up to 0 again. Which will never happen. Notice, you'll never actually get complete blackness because that would correspond to no radiation, but you're seeing into the stars, so you're getting light no matter where you look. It's just that you're getting less light at the wavelength of the spectral line. Is the width delta lambda of a completely black line which has the same area under the curve as the actual spectral line. So in other words, you integrate the depth with respect to wavelength. And that'll give you the area, if you will, of the spectral line. And the equivalent width is the width of a completely black spectral line that would have the same area. So, in other words, so that I don't clutter my diagram too much, and I'll redraw it here. That's too light. If that rectangle has the same area as the line does, same area under the curve, then that then that spectral line spread in wavelengths is the equivalent width W. area of the rectangle is the area of the spectral line, and the width of the rectangle is the equivalent width of the spectral line. That makes sense. We have a question about that. Does that make sense, or do you have a question about that?
Oh,
Essentially,
no, that makes sense.
the same amount of light,
Yeah,
so to speak.
I like the graph, it's easy to read.
So that's one way to talk about the width. Another common specification is the so-called full width at half maximum.
Ooh, now I
FWHM.
finally get to know what the.
Right. Another measure of line width. And full width at half max isn't just used for spectral lines, it's used for in lots of contexts. Another measure of line width is the full width at half maximum sometimes we'll just say full width at half max. And the abbreviation is just FWHM, logically enough. Which is the separation in nanometers, or we might use angstroms, between the points at which the line depth is 1/2, between the wavelengths at which the line depth is 1/2 of its maximum value. I actually forgot to say of its maximum value in the notes. The line depth is 1/2 of its maximum value. So, for example, find that later. Let's say